Welcome to Calculus. Today we will investigate how to integrate definite integrals by parts. We'll take a look at three examples. Our first example is the integration from 0 to pi of the integrand e to the x times cosine of x dx. We want to approach this solution by the strategy of integration by parts. So just to recall how the integration by parts works, if I've got some integral of u times dv from our product rule for differentiation, we come up with this result. That's really equivalent to u times v, the two original functions, minus the integral of v du. So again, what I want to do first is I want to select one part of the integrand to represent the u, and then another part of the integrand to represent the dv. So we want to do that first. And remember, there's a couple just guidelines that would help us to decide which part to assign. Typically, we let dv be the most complicated part of the integrand that fits a basic integration rule. So looking at what I've got here, I'm going to select dv as my e to the power of x. And then dx would always be associated with dv. And that leaves for me the other factor here, cosine of x, as my u. And again, the general guideline for u is let u be the portion of the integrand whose derivative is a function simpler than u. So cosine x will work. So with those assignments, let's set up our integration by parts. Again, I'm calling dv e to the x dx. So if I want to find d, I just need to integrate e to the x dx, and that's just going to be e to the x. And then if I've assigned u as cosine of x, then I want to differentiate to find du. And for us, that's going to be negative sine dx. So that's all set up. Now for this particular question, I want to keep in view my original integration. I am going to take the limits of integration off for now. We'll treat it as an indefinite integral first, and then we'll reassign those lower and upper limits, the 0 and the pi. But I'm going to write the integration of e to the x cosine x dx equals. Now I'm going to pick up with my right-hand side of the integration by parts formula. So that's u times v. So cosine of x, which is my u, times e to the power of x, which is my v, minus the integration of v du. So that's e to the power of x times negative sine x dx. And that sets up our integration by parts. So now what I need to do is just work on this second integration. So again, the integration of e to the x negative sine of x. So on my next step, again, I'm keeping that left side intact. I need to do something with it in a moment to combine like terms. So I'll keep that integration of e to the x cosine x dx equals, I'm going to move e to the x out front, cosine of x. And then I want to run integration by parts a second time, because if you notice, it's really the similar setup in my second integration. I will let that minus on the inside migrate out and combine with the minus on the left of the integration. So that's going to resolve as a plus. And then I need to set up a second round of integration by parts. So again, I'm going to do it similarly. My second round, I'm also going to assign dv still as e to the x dx, which implies that v again is just e to the power of x. U here is going to be just sine of x. And if I take the derivative of sine, that's just cosine x dx. So again, I'm going to run it And what we're going to see is a reappearance of the original integration question. So let's set it up first. So again, it's u times v sine x times e to the x minus the integration of v du. So that's e to the power of x times cosine x dx. Now, as I bring this green binomial out of the parentheses, I can pretty much just let the parentheses go since there's no coefficient out front. And what I notice is that these are identical integrations. The original question, integration of e to the x cosine x dx, same as minus integration e to the x cosine x dx. So what I want to do, and it's an unusual strategy for integration, I want to add that over as a like term to the left side. It'll cancel here on the right, and that has the advantage of really saving us from kind of a continual cycle. If we just kept doing integration by parts, this would just keep changing from e to the x cosine x to e to the x sine of x. So it cancels there on the right. If I add that here to the left, I've got two of the same thing. And so as I add those, that's going to become 2 times the integration of e to the x cosine x dx. And then I've got left e to the x cosine x plus e to the x sine of x. And to finalize at least the indefinite integral here, I would divide by 2. And that I'm going to just let show up as a factor distributed of half there. So that completes the integration. At that point, if this was an indefinite integral, I would put plus c, but we are trying to evaluate from 0 to pi. So let's put those limits of integration back. Go ahead and put 0 to pi. And so what that's going to equal, we're going to get rid of our c. And instead, let's set this up using fundamental theorem of calculus. So this is now 1/2 times, so we'll put in pi first, e to the pi cosine of pi, and then a repeated version, but now a sine, half e to the pi sine of pi. And using fundamental theorem of calculus, we'll subtract from that the same expression evaluated at 0. So half e to the 0 cosine of 0 plus half e to the 0 sine of 0. So we just need to evaluate that. We do have some cancellations at 0. At 0, sine has the value of 0. So this whole term we just wrote will cancel. This term, half e to the 0 times cosine of 0. Cosine of 0 is 1. E to the power of 0 is 1 times half. So this is just minus half from that second substitution of the lower limit of integration. Now let's work on the first substitution, which was pi. So sine at pi is also 0. So this whole term there is going to 0 out. And then cosine at pi is -1. So this is going to be negative 1/2 e to the pi. And that finalizes our evaluation of this definite integral, -1/2 e to the power of pi minus half. So that example, we did have to do integration by parts twice and use that strategy where we keep in view the original integration. Let's take a look at a second example that involves secant x tangent of x. So this is the integration from 0 to power over 4 of x secant x tangent of x dx. So again, what I want to do is decide which parts I'm going to assign as u, which parts I'm going to assign as dv. And I'm going to choose the part for dv first that I can easily find an antiderivative for. So this secant x tangent x dx, I'm going to assign that whole term there as my dv, which leaves for my u just the x. So we'll start with those assignments. So again, we'll begin dv is secant x tangent of x dx. So that implies that v, if I integrate secant x tangent x dx, that's going to give me secant of x. That's the antiderivative for secant x tangent x. For our u, we'd assign just plain x. So if I differentiate u, that's going to give me dx. So we're ready to set up. Again, if I've got the integration of u dv, that equals u times v minus the integration of v du. So we'll set up this right side. Let's substitute values in. So my u is going to be x. My v is secant of x minus the integration of secant of x dx. So we're essentially done at that point. What I need to do now is just integrate secant x dx. So up till now, we haven't had that in terms of one of my anti-differentiation rules or my basic integration rules. So over on the side, we need to build how do I find the integration of secant of x dx? And the way that we do that is we start off by just noting that if I write a sum, secant of x plus tangent of x, and if I identify that as a u, then what I can do at that point, what I can do is take the derivative. Again, I'm creating this in a way from scratch. So that's why I've got this kind of synthetic setup. So I'm assigning u as secant of x plus tangent of x. And I'll take the derivative of both sides. So here, in fact, what I want to do is I'm going to write that this is d dx of secant x plus tangent of x. So in general, that's just going to be u prime, since I've identified. In fact, let me write this up here. U is secant of x plus tangent of x. So if I actually take the derivative of secant of x plus tangent of x, I'm going to get secant squared of x plus secant of x tangent of x. Now, what I can do is factor this right side. I see that I've got secant of x as a factor of both. So that's secant of x times secant of x plus tangent of x. Well, at that point, what I've got here is essentially, again, u. So I'm going to make a substitution back in, keep u prime in view. So u prime equals secant of x times u. And then if I divide, I get this structure on the left, the derivative of u divided by u. Well, that's the same pattern that I would use for the natural log of u. And that's going to equal the secant of x. In fact, this is going to be the derivative of natural log of u. And at that point, what I can do to both sides, if I just keep in view what I'm trying to create, it's the integration of secant of x dx. Well, I've got secant of x there on the right side. And in fact, I should have a dx because I took the derivative. That is set up at this point for me to create my rule. And essentially, I just need to integrate both sides. When I do so, that right side looks exactly like the integral I'm trying to define. And what it equals is here on the left. So I'm going to switch things around. It's going to be the integration of secant of x dx equals, if I integrate the derivative of natural log of u, that's just the natural log, and putting back in u, that's secant of x plus tangent of x plus c if it's an indefinite integral. So all that to say, here's our rule for integrating secant of x. It's equivalent to the natural log of secant of x plus tangent of x. So let's use it. We created it so we could use it. So this is now going to be x secant of x minus the natural log of secant of x plus tangent of x plus c. If I'm considering this as an indefinite integral, it is a definite integral. So now I want to place back my limits of integration and use fundamental theorem of calculus to evaluate. So I'm integrating from 0 to pi over 4. And I see I've got some trigonometric ratios here. So let me just define those for these values. Secant at pi over 4. So that's the 45 degrees there in quadrant 1, has the value of the square root of 2. If I also check for tangent at pi over 4, that has the value at 45 degrees of 1. And then the other values I'll need, secant at 0 is going to be 1. Tangent at 0 is going to be 0. So let's set those in place now for the definite integration. So this is going to be pi over 4. Start with the upper limit of integration, substituting in for x times secant of pi over 4 minus the natural log of secant of pi over 4 plus tangent of pi over 4. And then I'm going to subtract from that. I'll just keep brackets around that whole first expression minus the same expression evaluated at 0. So 0 secant of 0 minus the natural log of secant of 0 plus tangent of 0. So we're ready to evaluate. We've got everything plugged in now. We just need to come up with our values. So from the purple expression, it's going to be pi over 4 times secant of pi over 4 is square root of 2 minus the natural log of secant of pi over 4 square root of 2 plus tangent pi over 4 is 1. Picking up with the red part, the first piece is going to zero out, and then the double negative is going to become plus natural log. Secant at 0 is 1 plus tangent is 0, 0, so natural log of 1, and that itself has the value of 0. And so really that second term didn't amount to much. That's our value. Let's take a look at one last example that involves the natural logarithm function. So here I have a definite integral from 1 to the value of e of natural log of x squared dx. So just as with our previous 2 examples, what I want to do first is assign one part to be dv, one part to be u. So for this one, I appear to have just one term or one factor in my integrand. So the way I'm going to treat this is I'm going to call the natural log of x squared, my u. I can take the derivative of that pretty readily, which means my dv is going to be simply dx. So let's set that up according to the pattern for integration by parts. So again, I'll start with the dv. That's 1 dx. So by implication, if I integrate, v is going to be just 1. My u is the natural log of x squared. So to take the derivative, I need to use the chain rule. Since I have a composed function here, natural log of x within the quadratic function square. So that's going to be 2 as my whole power as a coefficient times the natural log of x to the power of 1. Then I need to take derivative of the composed function, the natural log of x, which is 1 over x dx. So just to clean that up, that's going to be 2 natural log x over x dx. Okay, so let's set up for our integration by parts. Again, if I've got the integration, and I will treat it as an indefinite integral first, of u dv, that's going to be equal to u times v minus the integration of v du. So we'll substitute our pieces in here. So u was natural log x squared times v is just 1 minus the integration of v1 times du, which is 2 times the natural log of x over x dx. And at that point, we want to deal with this second integration now. So again, what I've got here is let me adjust. I did the integration incorrectly. So you probably were watching and saying, why did you integrate dx to 1? That should in fact be x. So let me make that correction here in my substitution as well. That simplifies this a lot because I've got now a cancellation here. X divided by x is going to cancel out. So for my next step, what I'm going to have is still natural log of x squared. And I need to actually fit in instead of 1 here as well, an x. So got to backtrack and fill in here. Put that x first. Now I'm ready to deal with the second integral. So it's the integral of 2. I'll let the 2 pass outside the integral to the left of natural log of x dx. All right. So at that point, we're ready to take the integral here. So basically at this point, I need to run integration by parts a second time. We've seen that already in one of these strategies. So I want to take a look at the integral we just finished writing, and again, assign to ourselves a u and a dv. So for this one, my u, again, it's a function that I can take the derivative of. It's going to be natural log of x. And what that leaves for my dv for this second round of integration by parts is the dx. So we'll pick that up and run it again. Again, my u is natural log of x, dv is dx. We'll start with dv. And I won't make the same mistake twice. When I integrate that, that's going to be just x. Our u is natural log of x. If I integrate, or I'm sorry, differentiate to get du, that's going to be 1 over x dx. And we'll run integration by parts a second time. So this is going to be x times natural log of x squared minus 2. And then I'm going to fill in with my parts here. So again, it's the same pattern, u times v. So natural log of x times x minus the integration of x, which is my v, du is 1 over x dx. And with that second round of integration by parts, I have a cancellation, my x's again, and this is really ready to finish in terms of the integration. This is now x times natural log of x squared minus 2. I'll distribute through now x times natural log of x plus, I got a double negative there, 2. And as I integrate 1 dx, that's just going to be x. So that's, again, the indefinite integration. I could put a plus c there, but again, I want to evaluate it from 1 to e. So we'll set up now for this evaluation. We'll start by putting in the upper limit. So it's going to be e times the natural log of e squared minus 2 times e natural log of e plus 2e minus, now we're going to plug in 1 for x. So it's 1 times natural log of 1 squared minus 2 times 1 times natural log of 1 plus 2 times 1. So now we're ready to simplify. Let's start with this red group. So I see I've got some reductions here. Natural log of e is 1. 1 squared is 1. So that term kind of goes away. This is just e. Natural log of 1 is 1. So it's e minus 2e. And then plus 2e. So even there, I've got a cancellation. Negative 2e plus 2e is going to go. So all that comes out of that first evaluation is just e. We'll set up the second evaluation. So this is going to be a lot of cancellations because natural log of 1 is 0. So that first term will cancel, the second term will cancel. All that's left there is plus 2, which is going to attain the negative sign. And that finalizes this for us. This has the value of e minus 2. Thank you for joining for this investigation of integrating definite integrals by parts. See you soon.